Hello, welcome to the class. Today we will talk about triangle rasterization. So these are the class objectives today. First of all, we'll talk about triangle rasterizations using edge equations. And then we'll talk about some other related techniques about how you can interpolate some of the parameters like the color. Also, we will talk about the incremental algorithm to accelerate the overall process of the rasterization. Before we move on, last time we talked about the clipping and culling method. Some of them which include the view frustum, backbase culling, also this hierarchical culling technique by using the bounding volume hierarchy. Also, I went over your questions. Some of you actually have a very interesting question here. One of your fellow students asked how do we apply clipping and culling when we when we actually have this transparent part, right? And then obviously also how can we handle optical lenses to obtain some of this realistic view. So when you have the actual transparent triangle, then we can see through some other actual triangle that are located behind this transparent triangle, right? So we cannot directly apply our culling techniques. So there could be basically there are a lot of when you think about some other issues how we can actually handle this kind of transparent objects. So actually, if you Google it, if you Google transparent or the translucent objects, there could be a lot of techniques. But in order to handle those kind of techniques, we need to use the ray tracing techniques. So we will to answer these questions. Actually, later on we'll talk about some of these ray tracing techniques. Also, one of your fellow students mentioned that there got to be the multi-threading programming, based this programming to utilize the GPU. But he or she said that up until now there doesn't seem to be any multi-threading in the source code. How can you actually utilizing the GPU or how you can do this parallel programming, right? So basically, that's the main benefit of using OpenGL. It seems like you are not using the multi-threading at all, right? But under the hood of the OpenGL, we are using actually multi-threading. So if we do if we perform this kind of various transformations, actually there are not much dependency between the transforming a vertex, also this and this transforming another vertex. So basically we can actually very easily multi-thread and perform the we can actually do that process in a parallel way. Also, we don't need to show any kinds of complications related to this multi-threading to user who are using OpenGL. That's why it's very easy to use. That's why it's very easy for us to use the OpenGL. Basically, that's the main success, main actual reason why the OpenGL becomes why the OpenGL also the DirectX become very successful in parallel programming language. So that's why they're having a lot of effort and also the issues to design the kind of OpenGL or DirectX API. So if you're interested, why don't you Google and then look into that kind of issues. That also relate to this how we can designing very fast API also language that doesn't give you a lot of complications and also complexity to users who are using that library. Okay, thank you for bringing up this question. So before we talk about today's material, rasterizations, I will talk about these different coordinate systems. So once we define our model in each own model space, then we need to do this modeling transformation, right? Then the object coordinate in the world space. We do this viewing space, then the coordinate in the eye space, or we can call it the screen space. And then we do this projection, and then where we have this clip space, and then by this homogeneous divide, we are going to the NDC by doing this transport transformations. We can actually say that now we compute this coordinate in the window system, this screen space. So to differentiate this screen space and this one, I will say this eye space, and this one actually the screen space. So here at some point actually everything's actually performing the transformation on the vertex. At some point, we need to convert this triangle consists of the vertices into a set of the vertices. That actually happens in this rasterization. So rasterization converts the vertex representation to the pixel representation. Suppose that you have a line, this kind of continuous representation of line, then we need to actually define a set of the pixel to cover this line, right? But in our case, actually, we wanted to transform this triangle into a set of the actual pixels. Here, you can think that this is actually center of the pixel. So, for example, we need to decide whether this pixel, we need to decide whether we need to keep some color of this triangle into that pixel or not, right? So along that line, we need to actually two issues, how we can define these coverage determinations. So basically, there are certain overlap between this pixel and triangle. How we can, there are certain coverage of this pixel under this triangle, right? Then do we need to give the color for that pixel or not, right? Also, for this kind of the pixel, we know that the pixels are totally covered by this triangle, right? We need to give the color of this triangle to that pixel, right? But in this case, this triangle actually has one color. But what if we have the actually varying color? What if we have the three different color on each vertex? How can you compute the actual color within that pixel, right? That's related to this parameter interpolation. So section, I will talk about what are these coverage determination parameter interpolations. I will move on to the next one. So coverage determinations, actually, in a way, it's a 2D sampling problem, right? Since the pixel is nothing but some sort of rectangular shape, triangle also there has another one. But thinking about this coverage determination between these 2D shapes, it actually turns out very complicated. So actually, commonly we reduce the problem into 1D sampling problem. In other words, we're checking a sample point. In this case, we check whether this center pixel, the center of the pixel at the sampling point. We plug in the sampling point, whether that sampling point within this triangle or not. Since this sampling point of this pixel is outside of this triangle, we said that basically this pixel is not relevant within this triangle. So basically, I will talk about this 1D sampling problem here, but there could be there has been many other techniques so far. One can actually measuring the distance between the primitive to the sample point. Also, there are % of coverage of the pixel, which is still popular. But right now, actually, we will pick this very simple 1D approach. We actually plugging the center of the pixel point and check whether that's the inside or the triangle or not. And then there could be the many different ways of performing this rasterization. But in this class, we will mainly talk about the rasterization technique with edge equations. So here, the main idea is that given these three vertex of this triangle, once we actually transform all those vertices into the empty space and also this screen space within this pixel space. Then we compute this actually edges out of these three vertex, right? And then we actually make sure that the center, the number of edge actually heading the inside of this triangle. And then we actually here we set up this edge equation first of all, and then we traverse pixel, evaluate this edge equation, and then we draw pixel. Which actually turn out to be the inside of this triangle. In other words, they give us the positive positive value for edge equation within this region. And then we in this case also we compute actually the color. In other words, we interpolate various attributes at those pixels. These are actually the high level ideas that I can talk about along the rasterization technique with edge equation. First of all, we need to actually set up the edge equations out of the three vertex here. So these are suppose that here we want to compute the one edge equation from the vertex 0, vertex 1. That could be the many different way of computing the actual edge equation. But we can just using the cross product between these here actually we treated this v0, v1 as a homogeneous coordinate, something like this v0 coordinate, x0, y0, n. And then by doing the cross product between these two vertex, will generate the actually the normal of this line, and then that way we can compute this line equation. It seems to be a little bit it is not the intuitive way, but actually you can treat that, you can think about it is actually you can think about it the mapping mapping this you can think about it is the 3D homogeneous coordinate then mapping to this 2D space, right? Then for this homogeneous coordinate, there could be the line passing through the line passing through this point, right? Here the homogeneous line actually that are projected to the same points once we do the homogeneous divide, right? So you can think that there's a line passing through the origin of the space, or there could be another line passing through this one. Then this line, basically the mapping to the plane. Then you can see that actually this normal, by performing cross product between this normal, that normal, which is nothing but this point and this vertex, then you can compute actually the normal of the plane. So that's why we can actually have this kind of equation. If you are actually there, in my book, there could be there are actually more detailed explanations. So by performing cross product here between these two vectors, then we actually get this information. But here actually we say that this ABC coordinate here sometimes I may use the 0, 1, mainly because that this actually the edge coefficient, I would say this edge coefficient ABC coming from the vertex between the V0 V1. And then basically this edge equation, we can compute it basically the dot product between this coefficient with the point x, y, and 1. Basically edge equations then can be represented by these equations. And then when the point under this line, then if we plug that point into this edge equation, it will keep the 0. But basically, by definition of here, if we treat the pixel actually within the inside, when we plug that pixel against this edge, it gives this positive value. So that way we define this normal that way. So basically, we follow this assumption here, that configuration. Then actually we set up these edge equations. There could be many other ways, but actually based on this, actually we can accelerate this. We can actually very compactly, we can very efficiently perform this rasterization process. I'll get back to that issue later on. And then there could be some other these complications. Suppose that there are two triangles that are passing through this pixel, but actually they are passing through exactly the center of this center of this pixel. So two triangles share this edge. This actually triangle 1, triangle 2, but they're actually having the different color. Then what are they actually do? Then when you plug in this center of this pixel into the edge equation of this triangle, it will give the 0. Same thing happen with the triangle 2. Then what kind of color we have to choose for that pixel, right? That's the issue. So if we actually if we adopt when you actually have the edge equation turn out to 0, if you allow that if you assign this color of triangle into that one for both of case, then pixel color becomes dependent on the order of the triangle rendering order, right? If we actually render triangle 1 first, it becomes the red, and then if we rasterize this triangle 2, it will then change the color from red to the blue, right? Obviously, we don't want that kind of dependency, right? Also, when we actually also create the problems when we rasterizing, rendering transparent object, right? Double hitting, right? Then it will complicate a lot. So if we also another choice is that we don't assign any color, then obviously it will create hole, right? So actually these are not good solution. So we need in this case it's nothing but just tie case, right? So we need a kind of consistent way of breaking this tie. So actually we need a tie breaker. You can think about it many other options. One simple tie breaker is like this. After suppose that we actually think about the normal of this edge equation. Out of ABC, we only look at AB. Then if the A is not the 0, then we take we actually A becomes the positive. Then we'll actually treat it will be there's some sort of boolean variable, and then we just when you actually header the non-zero A, it will becomes the 1, right? So in that case, actually, the a corresponding to a corresponding to x coordinate. So this then actually only the triangle 2 becomes actually the positive for that one. Then our coverage determination becomes like this. Edge equation turn out to be the bigger than positive, or when the edge equation turn out to be 0, then in that case we should have the positive value. Then in this case, the triangle that located along that side, having the normal along that one, then we will get the color here. Also, there could be the other the special case. So for the somehow not the in this case actually before actually the edge passing through the center pixel. Now the vertex of the triangle actually somehow located at the center pixel. Then also we can use another tiebreaker, like we actually check the triangle that passing that actually they're located within that direction, right? Based on in a similar way like this. Also another approach is that basically this problem, right? So actually we actually prevent this problem. In other basically to do that, to prevent this problem, we snap vertices to subpixel grid. So somehow we define the subpixel grid in a way that and that displays this vertex into one of this closed grid in that subpixel grid. So that actually when you testing this vertex with the edge equation, then there's no way that actually it turns out to be at the cases. There could be the many other cases. Actually, they try it out. Actually, the NVIDIA and many other companies actually they try it out their different approach, and then they implement a technique that give us the best performance. So I talked basically based on this one, we know that actually given this equation, we can know that whether this pixel is actually within this triangle or not, right? In this one, if we plug in the pixel here against this three equation, it will give the positive all of these three positive values, right? Then we know that what are actually the pixel within this triangle. The next question is that how can we compute actually the color? So hold that this actually our screen. This the three vertex here. Now I got the color here, some value, some another color. So here I'm mainly looking into the color channel, mainly this red channel. Same machinery can be applied to the other channels, right? But the color actually varies here. But basically we are only given the three color at each vertex, right? How can you compute the color within this triangle, right? So there could be the many different approach, but one simple approach is that we just treat the linear interpolation basically from these three vertex, right? So in other words, we actually this actually they're indicating is how the level of the readiness, right? And then we actually treat that the color actually the color changing linearly among these three vertex. So actually we can treat that the linear plane, the planar function there. So actually this red value, this value actually we can represent that equation as some sort of this plane equation where we actually have these three coefficients. I would say AR, DR, CR. They are actually corresponding to the coefficient of the red channel. But there are actually three parameters to represent this equation. But fortunately we have the three vertex, right? 1, 2, 3 vertex. Actually, we can compute the three unknowns. So if we set up this equation, so here these are the actually three vertex here. Then by performing this coefficient with that vertex, we know that actually what are the red value at that vertex, right? But we can actually do we know what are the color value R0, R1, R2 across these three different vertices, right? So that starting from this equation, then if we actually if we apply invert of this matrix, then this equation can be represented by if we take the invert of this one, we can actually have this kind of equation. I guess you might some of you may remember actually the inverting this 3x3 matrix. Actually, if we do that, actually we can have this kind of equation like this. It's a little complicated, but we can actually have this kind of solution. But now let's look at, but actually there actually there are a lot of relationship between this equation, some other relations here. For example, let's look at the round area. Let's look at this triangle area. There are also many other way of defining triangle area. One way is to using this determinant. So the 1 over 2 multiplied with determinant of their vertices can actually we can, based on this one, we can compute the area interpolation at the triangle area. And then these actually can be computed by something like this. And then there could be a lot of the multiplication between x and y with some of these different vertex. But surprisingly, actually, if you look at this x1, y2 minus x2 and y1, this is actually nothing but this is nothing but the edge equation coefficient that are corresponding to c. I would say this is c0, c1, c2, but actually they're here x0 and y1 minus x1 y0 is actually nothing but coefficient here, coefficient that we computed with the education out of this v0, v1, something like that. So, that is nothing but for this coefficient I just say that this is the c2, something like that. So in other words, these three terms actually coming from the three different educations along this c coefficient. So in other words, once we set up the education, area can be computed by just addition of this coefficient, right? And then also there could be some other optimization here. When area turns out to be 0, it means that triangle is not visible, right? Then we stop the rasterizing this triangle, right? Since there's no area for the triangle. And then area becomes in this case, area becomes 0. It means that triangle actually back facing. If we see that, if we actually do this process of the visible triangle, in other words, it's normal heading toward you, then it becomes the positive value. But the triangle that has the other normal, it becomes negative 1. Then it's the actual back facing triangle. Then here actually we can do the actual back face calling, right? And then we can do the reject triangle if we perform the back face calling. Otherwise, if you don't do the back face calling, then we actually we actually flip these educations and then do the other operations. So bottom line is that here with this equation to compute this color interpolation, we need to have some sort of determinant here, but this determinant already shared by this area, right? And this area also can be computed by the sum of the coefficient of the education. In other words, we can very efficiently actually process this operation, that operation. Now how about this one? Now some of you can already see that pattern, right? This actually exactly mapping to the coefficient of the education, right? If you see that the coefficient of this education here, the delta between y, delta of x, and the sum of this combination between x and y. And then you can see that actually that one is mapping to here exactly. In other words, these are also mapping to the coefficient of the three different educations. So in summary, basically the coefficient of the readiness channel of this red plane AR, BR, CR can be computed by this actually the color value R0, R1, R2 at the three different vertices, and then these are the actual coefficient of the three different educations. So I actually used this term. So this is actually basically we write down the three different education at that way. These are actually the vector of the educations. Then we know that actually this coefficient. Then once we set up coefficient, then given any vertex, we can compute the color, right? If we plug in that pixel location there, we can compute the color. Okay, so now let's move on to G buffering. G is nothing but a depth, right? So basically, when you actually rasterize this triangle, you can get this kind of color, right? In terms of RGB. But while we are doing the rasterization, we also need to do we need to compute the depth value, G value. So that actually G value is depth, so that actually given these two vertex, you can see this one, right? Basically this vertex give you the actually more smaller depth value, right? So given you might recall that our actually G buffer G value actually the initialized between the minus 1 to 1, and then 1 is actually far value, right? So in the end actually we also actually it's a complicated issue, but in the end we also process the G value between the 0 to 1. But anyway, 1 actually the object located more far away from you actually having the more bigger value along this line, and then at maximum case 1 is actually far value back into this far plane of your view volume. So based on this one, when you rasterize, when you do this kind of the rasterization, also the interpolating color, also you do the interpolating this G value of this each vertex and for each across each pixel, and then your new triangle has your G value smaller than the current G value stored at the current this depth wrapper. Then obviously you know that this actually the more close one to you. So that actually we updated that G value with the actually at the depth wrapper. Yeah, basically write that pixel to the pixel value. In other words, we updated color wrapper. Also we updated this G wrapper, right? That way we maintain actually only the visible triangle based on the G value, right? So that's actually the G buffering. So there are a lot of issues. I mean, there has been a lot of issues how we can define this visible triangle, visible the pixel out of this scene. But it turns out that actually this simple algorithm, this is actually the long time ago, maybe 30 years ago, 40 years ago, this algorithm known as the actually brute force algorithm, which is actually it doesn't have any intelligence, but because of simplicity of this technique, it turns out to be the method of choice right now. A lot of most of the GPU implement actually this G buffering technique. It turns out it's very simple. That's why we can actually design the hardwired chip to implement this idea. And then it turns out that this is one of the most dumb or the brute force algorithm turn out to be the method of choice right now. So basically, this G buffering, later I'll talk about that here. The ray tracing actually also can do this visibility algorithm. The G buffering, also the ray tracing, are the two different actual alternatives to perform the computing this visible triangle. But now actually G buffering actually mainly adopted for this rasterization, mainly for this performance. But ray tracing actually mainly adopted for the generating very high quality rendering, since you can also apply this, you can support all of these operations. Also, you can handle this transparent also the objects in a very easy way. For the G buffering case, supporting this transparent object is very complicated. So there are a lot of techniques, a lot of papers. For ray tracing, it's very easy to handle that kind of complicated actual effect, more complex rendering effect. Okay. So now, given this education, here this actually our screen space, and then how we can actually we need to traverse this pixel, right? And then we check that whether these pixels are within the triangle or not, right? So there could be the many different way of the traverse pixel, right? But one of simple one is that actually given this screen, we actually divide the screen space into the multiple tiles, and then first of all we check that whether this tile actually clearly out of this triangle, right? And then we knock this tile out. Then it means we don't do any operation there, right? For this one, this tile actually straddling with this triangle. Then we actually go over each individual pixel within the tile, and then actually we do that rasterization operation. Also, you can see that actually when you actually processing this tile here, and then there's no dependency between this tile, also the processing this tile, right? In other words, we can do this operation in a parallel way. But that's why this is also very commonly adopted in modern GPU for rasterizing this triangle. So now also we can actually right now actually we can see that there are a lot of optimizations to accelerating this rasterizing these triangles. Since there could be a lot of triangles, also given this triangle, here actually there could be a lot of pixels, right? If you assume that there are 1K by 1K resolution, there could be 1 million triangles, right? Then if we actually have a lot of triangles, actually we need to process actually a lot of pixels, right? That's why there could be a lot of optimizations. Another optimization is the incremental optimizations. So here, when you're processing this, suppose we process this pixel, right? And then we don't do the random ordering, right? Probably we actually process next pixel, something like that, right? Then suppose that edge equation at that x and y location, we actually evaluate this edge equation, right? And then based on the value of this, we can do a lot of operations, right? Now, if we actually reprocess the just next pixel, in other words, we testing x plus delta, just 1 unit away from the current vertex to next vertex, then you can see that actually, basically we plug in this equation here, x plus delta here, byc, and then if we actually reformulate this equation, then it's nothing but edge equation of the prior pixel plus a delta, right? And also we can do the same operation along the y direction, right? Based on these actual observations, we can also more accelerate this process. For example, if we're just evaluating this edge equation to there, we need to do a lot of multiplication, right? But here we just one multiplication and plus one addition, then we can do the actually evaluate this edge equation. So saving up here actually the multiplication and also the addition, which turn out to be a lot when you actually when you're processing a lot of triangles, also a lot of actually pixels. Okay, so in summary, once you have the one triangle, you need to actually construct edge equations. There could be the 3 cross product, right? And then you do the triangle area. It can be done with a few additions. And color zero area. Also the color backface triangle if there's there is actually enabled. And or depending on the process, we actually flip the edge equation. And then we construct these interpolate equations. And this also can be done matrix vector operations. Then actually we traverse pixels, and then we compute we know what are the pixels within the triangle and compute the color for that pixel. Those are this X triangle setup, and then based on that we do the rasterization. So now let's think about it. There could be a lot of the triangle here. So actually a long time ago, so one of my research topic is the rasterizing, rendering a lot of this big model. This is the same metric model consisting of about 400 million triangles, a lot of triangles, right? Then think about it. If we just if we had 100 million triangles, and then if we had 1K by 1K resolution, there could be only 1 million pixels. It means that on the 100 visible triangles actually mapping to the 1 pixel here, right? When you rasterize this, a lot of the massive model, there are in other words, there are 400 triangles that mapping to 1 pixel, right? But how many triangles can you see? Just we can see only a few triangles, right? So in other words, it's a lot of the waste of the setting of the triangle, right? So for each basically we can only see only a few triangles, but actually if we just naively rasterize, sending this data to the GPU and rasterizing them, then obviously we waste a lot of time to specify these 3 vertices, 3 edge equation, and so on, right? So there could be the better way to accelerate this process. So actually, along that line, one of technique is actually the multi-resolution or the levels of detail, or the LOD techniques. Its basic idea is that this actually our viewer, if the model is located very close to the viewer, we cannot see. We can see that this a lot of the triangle, right? Then we should use the original method, original mesh, right? But if actually the model actually located very far away from the viewer, then maybe we don't need to use the original a lot of triangles, right? At that case, we can actually somehow simplify this model. In other words, we actually compute another set of the model with a fewer number of the triangles, right? And then so let's say this one actually has 1 million, but we can just if we can just use the 1K triangle, then instead of rendering 1 million, by using this one we can get a lot of the speed up, right? That's the main idea of the multi-resolution. And along that line, the polygonal simplification, mesh simplification has been studied a lot. This is one of the ideas. Along the polygonal simplification, we want to reduce given this original mesh, we want to reduce the number of triangles in that way while maintaining overall shapes, right? So actually there has been a lot of research, but one of the very simple operation is the edge collapse. So given this, suppose that we actually had this vertex and this kind of triangle, then we identify these two vertex, and then we collapse it here. We actually collapse these two vertex into the one here. Then by doing this edge collapse, we can remove these two triangles, right? By performing this series of this edge collapse, we can simplify this triangle. We can represent this triangle with with a new model with a reduced set of these triangles. Obviously, when you do this operation, we should not introduce a lot of the visual error, right? So there actually has been a lot of techniques along that line. So how can you use this approach? So this approach is this original mesh, and then we do the mesh simplification. We represent this model with the 1,000 triangle, also 2,000 triangle here at when you render this the model before we running our application like game, and then when at the runtime, if the model is located very far away, then at the case, if we can use this one without introducing any much of the visual error, we can just using this model instead of that one, right? And then if the model is located more far away, then probably we can use this one. So at the case, we switching using this model to that model. At the cases, we switching instead of the random this model, we actually using this one. But actually, if you play the sum of game, actually this kind of technique is known as static levels of details. There are different LOD. Actually, they are kind of static. We actually pre-compute this one at one time, depending on the distance between the viewer and this model. We switching using this model to there. At the case, actually, there are some of the popping artifacts. You can notice that when you play the game, sometimes actual objects looks like more bigger and smaller, right? You can see that they can popping artifact, right? Popping artifact. So that's actually issues of the static LOD, while it can give you the much better runtime performance. So there has been another technique like the dynamic simplifications. So here actually we actually dynamically changing this resolution of the model. So this is our viewpoint, and then we gradually changing this resolution such that actually the portion that are very close to the viewer, we are using the very fine original mesh representation. For the part that are located very far away, we are using the very coarse, and we do a lot of the simplification so that we use the much fewer number of triangles. So that's the kind of the dynamic simplification, provide smooth and varying LODs over the mesh. But it is a very nice idea, but actually computing this operation takes a lot of the runtime cost. So actually this is actually more commonly used. So, I mean, when you play the current game, you can see that this kind of menu of some of the popping artifact. And also what if there are so many objects like this? Here I may talk about actually how we can change the triangle, right? Based on these edge collapse operations, right? But what if we actually have a lot of the multiple objects? So when you see some of the scene from Pixar movie, you can see this actually there are a lot of this grass, right? How can you do that? There are many other also there actually we need to also to accelerate the random process of this approach. So there are some other different ways of simplification techniques. So if you're interested, I recommend you to look into this issue. Okay, so far I talked about the various rasterization techniques. So I hope that by now you can understand the triangle rasterization using the edge equations, and then we actually talked about the derivative techniques, how you can actually parameter interpolations, also how we can do the incremental algorithm based on the edge equations. So once you get the full understanding on the edge equation, some other one, you can understand this technique. This is a regular homework. Go over the next lecture slide. Watch 2 Figure of Asia video. Submit their summary before the Monday class. Also submit 2 questions within this whole semester. And next time I'll talk about illumination shading. And that's it. Thank you. Bye.